So today, we're going to tackle a massive question. How do we find meaning, purpose, and, a moral compass in a world that might not have a divine blueprint? We're going to dive into the humanist worldview, which is a framework for building a significant life that's grounded in science, reason, and our shared humanity. And really, it all kicks off with one huge challenge. This right here, this is the big one. It's the question at the very heart of the humanist perspective. If we aren't just handed a purpose from on high, does that mean life is meaningless? Well, the humanist answer to that is a hard no. But it does mean we've got to look for it in some different places. And we're going to start with the biggest picture you can possibly imagine. So to even begin to understand our purpose, we first have to understand our context. Humanism doesn't start with ancient texts. It actually starts with cosmology. It asks a simple question: where are we and when are we? Getting your head around this perspective shift is the foundation for absolutely everything that follows. What's just mind-blowing about this timeline is the sheer scale of it all. I mean, think about it. Starting from a single point of infinite density, this thing called the cosmological singularity, the universe just exploded outwards for nearly 14 billion years. Stars were born, they died, our little planet formed. And then, only in the last tiniest fraction of cosmic time, we showed up. We are profoundly recent arrivals to a very, very old story. And this is the crucial point. The humanist view finds deep, deep significance right there, not in some pre-written destiny, but in the incredible, improbable journey that led to us. The fact that we even exist at all, that we are conscious and aware on this small planet in a ridiculously vast cosmos, that, in and of itself, is a source of profound wonder. And that's our starting point for meaning. Okay, so let's shift gears. Let's pull way back from that cosmic scale and zoom all the way in to the individual. If the universe doesn't give us a purpose, then who does? Well, this is where humanism borrows a little something from existentialist philosophy, and it presents us with both this exhilarating freedom and, honestly, a pretty heavy responsibility. This famous line from the philosopher Jean-Paul Sartre, it's a real cornerstone idea, but what does it actually mean? Well, simply put, we show up first, and our purpose comes later. Think about it. Unlike a tool, we aren't born with some predefined function. We just exist. Our essence, who we are, what we value, our very purpose, that's something we have to create for ourselves. One choice, one action at a time. And this comparison just illustrates it perfectly. Think of a hammer. Its essence, its hammerness, is thought up before it's ever made, right? It's built to pound nails. But a person isn't like that. We're just born. And then, through our life, through our actions, our values, we forge our own essence. We get to define what it means to be us. But all this total freedom, it comes with a pretty profound sense of weight. The existentialists called it anguish. And it's not despair, not exactly. It's that deep gut-level realization that the responsibility for our lives is entirely our own. There's no script to follow. There's no one else to credit or to blame. It's a staggering thought, for sure. But it's also the ultimate source of our power to create who we want to be. Now, if existentialism gives us that stark reality of our freedom, humanist psychology gives us the optimistic toolkit. It's often called the third force in psychology, and it moves past some of the older schools of thought to focus on what humans are capable of at our absolute best. This whole framework is built on some really powerful core ideas. It sees people as fundamentally good, with this natural drive to grow and get better. It champions personal choice and responsibility, not as a burden, but as the actual path to becoming our most authentic selves. It's a process they call self-actualization. So this really drives home the idea that meaning isn't something you just find under a rock, right? It's something you cultivate. It comes from the inside out. From learning, from creating, from expressing who you truly are, and from striving to realize all your unique potential. Okay, so we've talked about cosmic wonder and we've talked about personal growth. But what about right and wrong? I mean, this is a huge question for any worldview. How does humanism build a system of ethics if there's no divine lawgiver? And look, that's a fair and critical question. If morality isn't just handed down from above, does that mean it's just a free-for-all? Well, humanism argues absolutely not. Instead, it suggests we can build really solid, reliable ethical systems using the tools we all have. And humanism offers this rich toolbox for doing just that, not just one rigid set of rules. We can use rational ethics to test our moral ideas against evidence, kind of like a scientist. We can use utilitarianism, trying to create the greatest good for the greatest number. We could focus on virtue ethics, becoming good people by practicing things like compassion and honesty. Or we can use the social contract, building rules that we would all rationally agree to live by. The common thread? They're all human-centered. So the big takeaway here is that morality doesn't have to be some mysterious or supernatural thing. It can be grounded in very human stuff: our ability to reason, our capacity for empathy, and our shared understanding that we all do better when we agree on some common rules for living together. All right, let's bring it all home. We've gone from the Big Bang to the human mind and all the way to moral philosophy. So, what does the day-to-day practice of creating a meaningful humanist life actually look like? It really comes down to a practical toolkit for living. First, we engage socially because deep meaning is rarely found alone. It's found by contributing to a community, to something bigger than ourselves. Second, we try to live mindfully, paying attention to the present moment instead of just letting life rush by. And third, we consciously embrace wonder. We look up at the stars and we never stop asking why. And this is so key. A humanist worldview means you have to get comfortable with not having all the answers. You're sort of trading the comfort of certainty for the thrill of discovery, and for the profound awe you feel when you just think about the mysteries of existence. The search itself becomes part of the meaning. You know, if there is one single idea to take away from everything we've talked about, this is it. This is the heart of the whole humanist project. Meaning isn't a passive treasure hunt where you just hope you stumble upon some hidden chest. No, it's an active, it's a creative, and it's a deeply personal act of construction. So, to sum it all up, the humanist path to purpose is really about taking ownership of your life and your actions. It's about looking at the stars and at a living cell with the same amount of awe. And it's about building your legacy through the positive impact you have on the people and the world around you. Ultimately, this entire framework brings us right back to a single, powerful, and very personal question. In the absence of a pre-written script for your life, the pen is in your hand. The choice, the freedom, and the responsibility are all yours. So what will you create? All right, let's just jump right in. For literally thousands of years, humanity has been asking this one enormous question. It's pretty much the question that drives all of physics. And in this explainer, we're going to get into our latest and honestly most mind-bending answer yet. I mean, what are we? What is everything around us really made of when you get right down to it? What are the ultimate fundamental pieces of nature? Well, the story most of us think we know, turns out that's just the tip of the iceberg.
Yeah, you probably remember this from high school science class, right? It's that nice, comforting story about what we're all made of. It's a really neat picture, breaking the world down into smaller and smaller bits. Kind of like one of those Russian nesting dolls.
You know the drill. It goes something like this. All the stuff, all matter, is made of atoms. You zoom way in on an atom, and you see a tiny little nucleus with electrons whizzing around it. Okay, zoom in on that nucleus, and boom, you find protons and neutrons. And if you could crack those open, you'd find even tinier things called quarks. So the big takeaway from that whole story is that everything, I mean you, me, the planet, the stars, the whole shebang, is just a different combination of 3 tiny little Lego bricks. That's it. The electron, the up quark, and the down quark. It's an incredible, beautiful, simple idea. But here's the thing. That simple, beautiful, comforting picture, the problem is, it's a lie. It's not really how the universe works at its deepest level. It's a great story, but it's not the truth. Okay, maybe lie is a strong word. It's more of a white lie. A useful simplification we tell people because, well, the truth is a lot more abstract. It's weirder and honestly so much more amazing. Because it turns out our best theories of reality, they're not about particles at all. So if it's not particles, then what are the real building blocks? They're called fields. Just try to picture this, a kind of fluid-like substance that's spread out everywhere in the universe, at every single point in space. And this substance can ripple and wave and change over time. That's a field. So here's the big mind shift. The old idea was that particles are like tiny little marbles, separate objects flying around. But the reality? Particles aren't things at all. They're just ripples, little bundles of energy or vibrations in that underlying field. So a much better way to think about the universe is not as a collection of things, but as this vast, restless ocean. And what we call a particle, that's just a wave, a temporary excitation on that cosmic ocean. And this is where it gets really cool. There's an electron field that fills all of space. And what we call an electron is just a little ripple in that field. Same for quarks. They're just ripples in a quark field. And a photon, a particle of light, you guessed it, it's a ripple in the electromagnetic field.
This whole radical new picture of reality has a name. It's called quantum field theory. And its central message is simple. Fields are the real deal. Particles are just the side effect. We are all just incredibly complex patterns of ripples on this universal ocean.
So if fields are the real building blocks, then that completely changes our periodic table of the universe, doesn't it? Instead of a list of elements, what we really have is a catalog of all the fundamental fields. And what's crazy is that all the normal matter we see around us, everything, is built from just a handful of these fields. You've got the electron field, the up and down quark fields, and another one for a weird little particle called the neutrino. That's it. That's the bedrock of our world. But then, nature does something really, really weird. For reasons we have absolutely no clue about, it basically just copy-pasted that whole pattern. Twice, creating two more sets of heavier, unstable copies of those fields. Why? It's one of the biggest mysteries in all of physics. Okay, so you have all these matter fields, but they don't just float around ignoring each other. They interact, they talk to each other, and they do that through four fundamental forces. And guess what? Each of those forces is also a field. You've got gravity, electromagnetism, and then the two nuclear forces, the strong and the weak. And then, in 2012, the final, crucial piece of the puzzle slammed into place. After decades of searching, scientists at the Large Hadron Collider finally found it, the Higgs field. This is the one that gives other particles their mass. It's a huge deal. So you take all of that, the matter fields, the force fields, the Higgs field, you put it all together, and what do you get? You get what physicists, in a moment of stunning understatement, call the Standard Model. But really, it should be called the greatest theory in the history of human civilization. And you might ask, why such a grand title? Because it works. It works so well, it's almost scary. I mean, some of its predictions match what we measure in experiments to an accuracy of 13 significant digits. That's just insanely precise. It's a staggering achievement, for sure. But, and this is a big but, we know this isn't the final answer. We know for a fact that the Standard Model isn't the whole story. The book isn't closed. How do we know? Well, all we have to do is look up at the sky. When we look out into the cosmos, we see these giant puzzles that the Standard Model just has no explanation for. Things like dark matter, the stuff that's holding galaxies together, or dark energy, the force that's making the universe expand faster and faster. Our best theory has nothing to say about any of it. And that's where the Large Hadron Collider, the LHC, comes back into the picture. After its big success finding the Higgs, they upgraded it to smash particles together with even more energy. The hope, the dream, was that we'd start to see new particles, new fields, hints of the physics that lies beyond the Standard Model. So for years, they've been running it at these incredible new energies. And what have they found? Absolutely nothing. Zilch. Nada. Not a single new particle. All of our clever, beautiful theories about what should be next, nature just isn't playing along. The Standard Model just keeps on working perfectly. Now, you might think that's a huge bummer, a failure. But for a lot of physicists, it's the exact opposite. It's exciting because it's when we're proven wrong, when our expectations are shattered, that we're forced to get creative and really start making progress. So that's where we are now, in this incredibly strange and exciting position. Our greatest theory is more solid than ever, but we know it can't be the final word. The path forward is a total mystery. We're staring at a blank wall, which forces us to ask the biggest question of all. What lies beyond the fields?
You know, our sun, it feels so permanent, so constant. But its story is an epic one, 13.8 billion years in the making. And to really understand where our star came from, we have to go back, way back, all the way back to the very first moments of the universe itself.
So where do you even begin a story that big? Well, it doesn't start with a star or galaxy or even an atom. Nope. The story of our sun starts with the event that created space and time itself in the very first, tiniest fraction of a second after the Big Bang. Before anything we would recognize existed. There was expansion. But listen, this wasn't some gentle unfolding. It was an impossibly fast, universe-defining explosion of space itself. There's this incredible idea called cosmic inflation, and it goes like this. In a sliver of a second, so small I can't even describe it, the universe went from being smaller than an atom to, well, astronomically huge. It was all driven by this mysterious energy that acted like a kind of anti-gravity, pushing everything apart at a truly mind-boggling rate. This moment set the stage for, well, everything that followed.
And, inflation isn't just some wild guess. It's a really powerful theory because it neatly solves some major cosmic headaches. It explains why the universe looks the way it does. It stretched everything out so vast and so fast that it smoothed out all the wrinkles and evened out the temperature, basically creating a perfect, uniform canvas for the cosmos to get to work.
Okay, so you've got this super smooth, rapidly expanding space. But here's the thing about the quantum world. Nothing is ever perfectly still. On the tiniest scales, there's always this fizz of random energy fluctuations. It's happening constantly, everywhere. And this is the magic trick. Inflation took those microscopic quantum jitters and stretched them, really stretched them, to astronomical scales. Those tiny little flickers of energy, they became the seeds for all future structure. They are the blueprints for every galaxy, every star, and every planet that would ever exist. Amazing, right?
So, after that initial crazy expansion, the universe was this unbelievably hot, dense soup of energy. And inside this primordial furnace, the very first ingredients of our sun were about to be cooked up. For the first few minutes, the entire universe was basically one giant nuclear furnace. And it created the lightest elements, leaving us with a cosmos made almost entirely of hydrogen and helium. But notice what's missing. There's no carbon, no oxygen, no iron, the stuff needed to make planets and, well, us. That hadn't been created yet. Now, inside that tiny little other slice is something called deuterium, a heavy version of hydrogen. Its survival rate was super sensitive to how dense the early universe was. So by measuring how much of this cosmic fossil is left today, we can calculate with incredible precision just how much raw material the universe had to work with to eventually build the first stars. It's like a cosmic measuring stick. All right, let's jump forward in time. We're now about 379,000 years after the Big Bang. The universe has been expanding and cooling this whole time, and it's leading up to one of the most important moments in its entire history.
See, up until this point, the universe was just this thick, opaque soup, a fog. Light particles, called photons, were just ricocheting off of electrons like pinballs in a crazy cosmic pinball machine. There was no way to see through it. It was literally like being inside a star. But as the universe cooled down enough, electrons and protons could finally grab onto each other and form neutral atoms. And just like that, poof, the photons were free, the fog cleared, and for the very first time, light could travel across the cosmos without being stopped. This is the oldest light we can possibly see, the cosmic microwave background.
Now, when we look at this ancient light, it is astonishingly uniform. The temperature differences from one spot to another are tiny, just 1 part in 100,000. But those minuscule ripples, they are everything. They are the direct pictures of those quantum fluctuations from the dawn of time, now stretched across the entire sky.
So the first light is released, and a really strange new era began. The universe was see-through, but it was empty. There were no stars. The lights essentially went out, and the cosmic dark ages began.
Yeah, for over 100 million years, the universe was just dark. But it wasn't sleeping. In the quiet and the dark, gravity was patiently doing its thing, slowly pulling together the slightly denser regions of that primordial gas, setting the stage for the next great act, the cosmic dawn. And those first stars, which scientists call population 3 stars, were nothing like our sun. They were absolute monsters, hundreds of times more massive, made of nothing but pure hydrogen and helium. They lived fast and they died young, exploding in spectacular supernovae. And these explosions were crucial because they seeded the cosmos with the very first heavy elements, carbon, oxygen, iron, the raw materials for every generation of stars to come, including ours.
So, those first stars lit up the universe again, finally ending the Dark Ages. Now the lights are back on, the first heavy elements are floating around, and the long, messy process of building galaxies like our Milky Way can finally get started.
You see, galaxies aren't just built, they're assembled. The leading theory is called hierarchical formation, which is a fancy way of saying cosmic cannibalism. Seriously, small galaxies form first, and then over billions of years they crash into each other, merge, and build up bigger and bigger structures. Our own Milky Way is the result of countless mergers like this.
And we can even see the evidence of these ancient smash-ups. One of the biggest was a merger about 11 billion years ago with a galaxy that astronomers have nicknamed the Kraken. How cool is that? This epic collision was a key step in building the Milky Way we see today, helping to form its thick, starry disk.
Okay, so after billions of years of cosmic expansion, element forging, and galactic collisions, the stage is finally set. The Milky Way is grown up, it's full of heavy elements from generations of dead stars, and now a quiet little corner of the galaxy is about to become our home.
The birth of our sun wasn't some peaceful, quiet event. It was actually triggered by the violent death of another, much more massive star. A nearby supernova sent a powerful shockwave ripping through a huge cloud of gas and dust. This cosmic ripple squeezed parts of the cloud, giving gravity just the little nudge it needed to take over, collapse the material, and ignite a brand new, hot, dense core, our infant sun. When you think about it, it's just incredible. From tiny quantum jitters in the first second of time to the explosive death of some long-forgotten star, every single step was necessary to create our sun. It's this profound cycle of cosmic death and rebirth. And it leaves you with a final thought, doesn't it? One day, our sun will also die, and its ashes will be scattered back into space. What new stars and what new worlds will one day be born from them?
Have you ever really stopped to think about how our world, this, vibrant living planet, actually came to be? The story, it's not a gentle one. It's this wild tale of cosmic dust, insanely violent collisions, and a series of just incredibly fortunate events. Okay, let's dive into the unbelievable story of how our planet was born.
It really all boils down to this one question. How did a chaotic swirl of gas and dust just orbiting a brand new star somehow transform into the complex, life-sustaining planet that we call home? That's the puzzle we're going to unpack right now.
So our story kicks off with the raw ingredients. Long before there were any planets, there was just this vast, spinning disk of gas and dust around our young sun. And right there, within that disk, a kind of cosmic blueprint for our solar system was being laid out. And right from the get-go, our solar system was basically split in two. I mean, you can see it right here. There's this super clear divide between the inner, rocky worlds, like ours, and the outer, icy gas giants. And this was no accident. It was all because of a fundamental sorting process that was happening. And that sorting process, it's called the condensation sequence. The best way to think about it is like a chemical sorting hat, super close to the hot young sun. Only the heavy stuff, rocks and metals, could actually solidify. But way out where it was much colder, ices could form. This right here is the critical point that determined what our planet would even be made of.
And here's the dividing line itself, the frost line. Beyond this boundary, which was somewhere out between where Mars and Jupiter are today, it was finally cold enough for water ice to freeze. This gave the outer planets a massive amount of extra solid material to work with, which is exactly why they grew into giants. Meanwhile, inside that line, planets like Earth had a lot less to build with.
Okay, so let's get to the next phase, which was, it was anything but peaceful. It turns out the biggest planet in our solar system played the part of a cosmic wrecking ball, and in doing so, it solved a major mystery about the inner planets.
And that mystery? Scientists call it the Mars problem. For decades, our models of how planets form just could not get Mars right. They kept creating a version of Mars that was way, way too big. It drove them nuts.
The specific question was this: why is Mars such a lightweight? It's only a tenth of Earth's mass, right? But every single computer simulation they ran suggested it should have grown to be at least half the size of Earth, maybe even a full-on twin. So what happened? Well, the answer seems to be the grand tack hypothesis. What this shows is that Jupiter didn't just stay put. It actually migrated inward, like a giant bulldozer, just clearing out and scattering all the material in its path.
It basically cut off the disk of planet-building stuff right around Earth's orbit, which effectively starved Mars of material before it tacked, kind of like a sailboat changing direction, and moved back out.
Okay, so now let's see how all of this leads to the final, incredibly violent assembly of Earth itself. This stage is all about cataclysmic collisions, including the one that gave us our constant companion up in the night sky.
And you might think this took forever, but it all happened incredibly fast. In just the first 100 million years or so, the gas disk was gone, Earth's core had already formed, and then the single biggest event in our planet's history went down, the giant impact that created our moon. But the classic story of that impact hit a huge snag when we actually got our hands on the moon rocks from the Apollo missions. Scientists started calling it the isotopic crisis. So here's the puzzle. If some Mars-sized body, they named it Theia, slammed into Earth, then the moon should be made mostly of Theia's leftover material, right? But chemically, the Earth and the moon, they're practically identical twins. They're made of the exact same elemental recipe. The chances of Theia being a perfect chemical match for Earth are astronomically small. So how is that even possible? The modern solution to this is just breathtaking. It's an idea called a synestia. The impact didn't just chip a piece off of Earth. It was so ridiculously violent that it vaporized both bodies into a giant spinning donut of molten rock. Within this crazy structure, all the materials from Earth and the impactor got completely mixed together before they cooled and condensed to form the Earth and moon we know today. Problem solved. And that cataclysmic impact did one more critical thing. It set the stage for Earth's most important defense system, a hidden engine deep inside the planet that would protect it for billions of years. That engine is the geodynamo. It's the process where the swirling liquid iron in Earth's outer core generates our planet's magnetic field. You can think of it as an invisible shield, and it is absolutely essential for life. But here we go again with another mystery. Recent discoveries show the core is actually so good at conducting heat that the traditional power source we always thought ran the dynamo, well, it might not be enough, especially not for the early Earth. It's like a planetary energy crisis. So what's been keeping this engine running all this time? Let's break down the suspects. The freezing of the inner core, that powers the modern dynamo for sure, but that process didn't kick in until much later. The real emerging hero for the early Earth seems to be something called magnesium precipitation. The theory is that magnesium got dissolved into the core during Earth's fiery formation, and as the core cooled, it started to precipitate out, providing this powerful stirring motion needed to drive the dynamo right from the beginning. And what's truly amazing is that for a while, Earth wasn't alone. The early moon had its own magnetic field, and since the moon was so much closer back then, their two magnetic fields actually connected. They formed this powerful coupled shield that protected Earth's fragile new atmosphere from the absolutely fierce winds of the young sun. So what's the big takeaway here? For at least 3 billion years that we know of, this magnetic shield has been up and running. It's been deflecting harmful solar radiation, allowing our planet to hold on to its atmosphere and its oceans, basically paving the way for life itself. When you step back and look at the whole story, from forming in just the right spot in a dusty disk, to being sculpted by a migrating gas giant, to a cataclysm that just happened to create our moon and kickstart our planetary shield, our entire existence is a product of absolute cosmic chaos and just incredible luck. Which really leaves you with one final lingering question. Just how many other worlds out there were ever this fortunate? All right, today we are going on a journey, and I don't just mean back in time. We're going to a completely different planet, one that just so happens to share our address. We're going to explore the first 2 billion years of Earth's history. This is the period that set the stage for, well, everything. So let's get right to it. Let's go back to the very beginning. So, when you think about the very beginning of our planet, what comes to mind? For most of us, it's the Hadean Eon. And I mean, the name itself, taken from Hades, pretty much says it all, right? It conjures up these images of just a relentless, fiery hellscape. You're thinking magma oceans, constant bombardment from space. It's the classic violent birth of a planet story. But what if that classic picture is, well, mostly wrong? Turns out the actual evidence, locked away in these tiny, almost indestructible little crystals, tells a much, much stranger story. It wasn't just some simple inferno. No, this was a world of bizarre chemistry, totally unique geology, and just planetary scale paradoxes. And that whole strange story, it kicks off with a real shocker. Just how unbelievably fast our planet got its act together. I mean, you can forget about a long, drawn-out, chaotic childhood. Earth's basic systems came online with just breathtaking speed. I mean, look at this timescale. It's just astounding. In only the first 200 million years, and that is a blink of an eye in cosmic terms, Earth went from being this ball of rock collecting more rock to having a solid crust and, this is the big one, liquid water oceans. And how do we know this for sure? We know thanks to these amazing little time capsules, zircon crystals found in Australia that are 4.4 billion years old. The chemistry of those crystals tell us they absolutely could only have formed in liquid water. Okay, but the fact that those oceans existed so early brings up our first major puzzle. Because how could Earth possibly have liquid water when our own sun was way, way weaker than it is today? This is a famous problem in geology known as the faint young sun paradox.
And here you can really see the heart of the problem. The sun was only shining at about 70% of its current brightness, so by all rights, the early Earth should have been a frozen snowball, just a complete ice ball. But the evidence is undeniable. There were huge liquid water oceans. So what gives? How on earth did the planet stay warm enough?
Well, the answer was a greenhouse effect on an absolutely colossal scale. You had intense, non-stop volcanism just pumping the atmosphere full of carbon dioxide. We're talking up to 1,000 times the levels we have today. Think about that. This massive CO2 blanket was just what the planet needed to trap whatever heat that faint sun was giving off, keeping things just toasty enough for liquid water. Okay, so we've got a warm, wet planet with a solid crust. But what was that crust actually doing? I mean, modern plate tectonics, with continents drifting around and crashing into each other, that hadn't really kicked off yet. The planet's internal engine was working in a totally different way.
For a long time, geologists have been debating two main ideas for what was going on. On one hand, you have the stagnant lid model. That's where the crust is just one solid, unmoving piece. On the other hand, you've got an early version of a mobile lid, which is more like what we have today, with plates moving and diving under each other. And for decades, honestly, the evidence was pretty murky. And then, once again, it's those incredible ancient zircons that gave us the answer. When we analyze them, they have these chemical fingerprints of what's called hydrous melting. Now, that's just a fancy way of saying they formed from rock that melted with water. And that is a huge clue. It means that somehow ocean water was being pulled deep down into the mantle, which sounds a lot like modern subduction, right? So what this tells us is that early Earth wasn't one or the other. It was a weird hybrid, a patchwork planet with some stagnant spots and some much more active zones. All right, and it's in these early, weird oceans that life gets started. At some point around 3.5 billion years ago, these tiny organisms, cyanobacteria, they figure out a revolutionary new trick, photosynthesis. And they start pumping out oxygen as a waste product. But this leads us to our next great mystery. For 1 billion years, 1 billion, absolutely nothing happens to the atmosphere. So the question is, where did all that oxygen go? To figure out what's going on, you have to understand this idea of an oxygen sink. The best way to think of it is like a chemical sponge. The early Earth was just full to the brim with stuff that would instantly react with and soak up any free oxygen the moment it was made. And there were 3 main culprits, 3 big oxygen thieves on the early Earth. First up, the oceans were just saturated with dissolved iron. Any little puff of oxygen came along, and poof, that iron would rust and fall to the seafloor. Second, you had volcanoes constantly belching out gases that would just gobble up any oxygen in the air. And third, the atmosphere itself was loaded with methane, which loves to react with O2. So for an entire 1 billion years, life just couldn't make oxygen fast enough to overwhelm these sponges. So what finally changed? What was the tipping point that let oxygen finally win this war against the sinks? Well, the answer wasn't just about life. It was about geology. The planet itself had to grow up. It had to mature before the atmosphere could fundamentally change. And here's the crucial insight. As plate tectonics got more efficient, the planet got way better at burying organic carbon, the remnants of all those dead organisms, deep into the mantle. It was basically taking the sponges out of the equation. This process locked away the very things that were soaking up all the oxygen. So with the sponges getting weaker and weaker, the constant stream of oxygen from those cyanobacteria finally had a chance to build up in the atmosphere.
And we actually have a smoking gun for this exact moment. It's amazing. For billions of years, rocks all over the world have this strange chemical signature in their sulfur isotopes. It's called SMIF. The key thing to know is that this signature can only form in an atmosphere with no oxygen. Then, around 2.4 billion years ago, it just disappears, gone, from the rock record, everywhere, forever. Its disappearance pinpoints the exact moment oxygen levels got high enough to form an ozone layer, which blocked the specific type of sunlight needed to create that SMIF signal. The tipping point had been reached. Oxygen was finally loose on the planet, and it immediately and violently reshaped everything. It created a world of both profound crisis and incredible opportunity.
So to get what happens next, you have to remember that methane-rich atmosphere, the one that was doing all the heavy lifting keeping the early Earth warm. Methane, as you can see here, is a way, way more powerful greenhouse gas than CO2. It was basically the planet's supercharged heating blanket.
Well, here's the problem. Oxygen is methane's mortal enemy. As those oxygen levels shot up, it just ripped through the atmosphere, destroying the methane, effectively tearing away the planet's main heating blanket. The result? A climate catastrophe. Global temperatures plunged, and the Earth was thrown into its first, and maybe its worst ever, global ice age, what we call the Huronian glaciation. So, in the end, oxygen was a classic double-edged sword. On the one hand, for all the existing life that had dominated for billions of years, life that couldn't handle oxygen, it was a deadly poison. It caused a massive extinction. But, on the other hand, for the few organisms that figured out how to use it, it was the greatest opportunity in the history of life. Breathing oxygen unlocks so much more energy than any other process. It's this new, high-octane lifestyle that paved the way for every large, complex animal to ever exist.
And so here it is, the whole 2 billion-year saga in a nutshell. You go from the shockingly fast formation of oceans to the slow, patient work of tiny microbes, all leading to that one geological tipping point that finally let oxygen loose. And then, the massive climate crisis that followed. It's this incredible planetary-scale transformation, all driven by this intricate dance between geology and biology.
Which leaves us with a pretty provocative final thought, right? Our planet's path to having a breathable atmosphere, the very thing that makes our lives possible, wasn't a guarantee. It wasn't inevitable at all. It depended on a very specific sequence of geological events, the right kind of geology kicking in at just the right time. So it really makes you wonder, how many other planets out there might have life, but they're just stuck behind a geological barrier, still waiting for their own tipping point, their own great oxidation event.
You know, when we think about Earth's history, we usually picture massive volcanoes or, planet-killer asteroids. But what if the single most powerful force to ever shape our world was actually life itself? We're about to take a journey through 4 billion years of history to see how life didn't just live on this planet, it built it, and sometimes nearly destroyed it.
So, let's start with a bit of a puzzle. What kind of force is powerful enough to plunge the entire Earth into a global ice age from millions of years, and then, in this incredible twist, create the very oxygen-rich atmosphere that makes our own lives possible? You might think it's a comet or some massive supervolcano, but no, the answer is biology.
And that really gets to the core idea of our story today. See, the Earth isn't just some static rock that life happens to live on, it's a deeply interconnected system. You've got the geology, the rocks, the volcanoes, the climate, and it's in this constant dance, this feedback loop with the biology. Everything from the tiniest microbe to the biggest whale. Life isn't a passenger here, it's a planetary-scale engineer.
Now, to really wrap our heads around this, we have to think on a totally different timescale. I mean, forget centuries or millennia. We are talking billions of years. We're going to travel through these vast eons of Earth's history, starting way, way back in the Archean, long before any complex animals ever existed.
So here's our roadmap. We're going to frame this whole thing as a grand planetary drama in 3 acts with a very modern epilogue. We'll start in an alien methane world, then witness a catastrophic oxygen revolution, journey through an age of massive extinctions, and finally, bring it all home to our own really unique moment in Earth's history.
Okay, let's set the stage for Act 1. We're going back to the Archean Aeon, over 2.5 billion years ago. The planet is, well,
It's basically unrecognizable. It's an alien world with no oxygen, and it's run entirely by simple microbes. And this early Earth faced a huge astronomical problem.
It's a famous puzzle called the faint young sun paradox. See, all our models of how stars work tell us that the sun, back then, was a lot weaker than it is today. It was only putting out maybe 70% of its current energy.
So what does that mean? Well, with a sun that dim, the entire planet should have been a frozen wasteland, just a solid ball of ice, right? But all the geological evidence we have shows that there were vast liquid water oceans at the time.
So what gives? What was keeping the planet warm enough? What was acting as Earth's thermostat and stopping it from freezing over completely?
And the hero of this story, believe it or not, was life itself. The earliest little microbes were anaerobic, they didn't need oxygen, and as a waste product, they just pumped out enormous, and I mean enormous amounts of methane. That methane created this super potent greenhouse blanket, trapping what little heat the faint sun was giving off and keeping those oceans liquid. For over 1 billion years, the entire planet's climate was stabilized by microbe farts.
And now for Act 2. This is where the story takes a wild turn. A brand new biological invention comes on the scene, and the hero of our first act, life, becomes the villain, unleashing the single greatest pollution event in the history of the planet.
So how did it happen? Well, it all started with these new microbes called cyanobacteria. They figured out a revolutionary new trick, photosynthesis. For the first time, something could use sunlight for energy. Amazing, right? But it had a toxic waste product, oxygen. Now, for hundreds of millions of years, this oxygen just got soaked up by things like iron in the oceans and other geological sinks. But, eventually those sinks just got full. The planet hit a tipping point, and suddenly free oxygen flooded the entire world.
The consequence was immediate, and it was catastrophic. Oxygen is super reactive, and it went straight for the methane that had been keeping the planet nice and warm. It completely shredded that greenhouse blanket, and the planet's thermostat just broke. Global temperatures plummeted, triggering the very first and the longest snowball Earth event, a deep freeze that might have lasted for 300 million years. Life literally poisoned its own cradle.
But here's the incredible twist. While this was a total mass extinction for the old anaerobic world, it was also an act of what you might call creative destruction. This new, oxygenated atmosphere opened the door for a much more efficient way to get energy, aerobic respiration. This is what paved the way for complex cells, for eukaryotes, and, well, eventually for us. It also created the ozone layer, which shielded the surface from nasty UV radiation, and that allowed life to finally crawl out of the oceans and colonize the land. Okay, let's fast forward to Act 3, the Phanerozoic, the eon of visible life. Now, this is a world we'd finally recognize, a world with animals, forests, dinosaurs, but as we're about to see, with all that new complexity came a brand new kind of fragility.
So first, you get the Cambrian explosion, this incredible burst of evolution that fills the oceans with the ancestors of basically all modern animals. Then plants and bugs conquer the continents, building these vast, intricate ecosystems. But here's the thing about all this new complexity. It also made the whole system incredibly vulnerable to really rapid external shocks. And the ultimate test of that vulnerability came about 252 million years ago. A truly massive volcanic event in what's now Siberia erupted for hundreds of thousands of years, just belching colossal amounts of CO2 into the atmosphere. This triggered what geologists called the deadly trio. First, runaway global warming. Second, the oceans suffocated as they lost all their oxygen. And third, severe ocean acidification. It was a 1-2-3 punch.
The result was the Great Dying. It is by far the worst mass extinction in our planet's history. Over 90% of all species in the ocean just vanished. It was a near total reset of the biosphere. And it's a terrifying warning of what happens when you rapidly inject huge volumes of CO2 into the Earth's system.
And that brings us to the epilogue of our 4-billion-year drama, right now, the present day. For the very first time in Earth's long history, a single species, us, has become a geological force on a planetary scale. The amount of carbon we're now pumping into the atmosphere is starting to rival the sheer scale of those great volcanic events from the past. And the stressors, they are hauntingly familiar. Warming, acidification. But when you look at the deep history of our planet, it reveals one critical and frankly terrifying difference.
And here it is. Look at the crucial difference. It's the rate of change.
The Siberian Traps eruptions, they were rapid in geological time, but they still played out over hundreds of thousands of years. Our emissions? We're doing it hundreds of thousands of times faster. We are completely overwhelming the planet's natural buffering systems, like rock weathering, that helped it recover in the deep past.
So, if there is one key lesson to pull from the ashes of the end Permian extinction, it's this. Our incredibly complex, interconnected global civilization and biosphere are not inherently resilient. In fact, that very complexity can be a profound vulnerability when it's faced with a shock that is as rapid and as powerful as the one we are currently initiating.
When you look back through these 4 billion years, you see this crystal clear pattern. Biological innovations, geological events, they all have consequences that reshape the entire planet. The story of Earth really is a story of actions, and they're often catastrophic reactions. And so the question for us now is pretty simple. What will be the ultimate consequence of our chapter in this incredible living history?
All right, today we're tackling an absolutely epic story. We're going back 66 million years to understand how our modern world even came to be. This is the story of the Cenozoic era.
So think about that for a second. What does happen when a planet's reset button gets hit? When 3/4 of everything is just gone? That's the core question here. It's not just a story about an ending, it's a story about a new beginning, about how life finds a way after a total, planet-wide catastrophe. And that's the thing, right? For our world to even exist, the old one had to go. And its end? Well, it was something straight out of a disaster movie. Fire, darkness, the whole deal. Okay, let's set the scene. 66 million years ago, an asteroid, about 6 miles wide, slams into the Earth. The impact is almost unimaginable. It's so big that it wipes out, get this, 75% of every single plant and animal species on the planet just gone. I mean, think about the dinosaurs. They ruled this planet for over 150 million years, and in a geologic blink of an eye, they vanished. The entire board for life on Earth was completely reset.
So this cataclysm has a name. Scientists call it the KPG extinction event. And you might be wondering, okay, but how are we so sure it was an asteroid? That's the amazing part. All around the world, geologists have found this thin, distinct layer of clay. And in that clay is a ton of iridium. Now, iridium is super rare on Earth's surface, but it's really common in asteroids. It's like the cosmic smoking gun, the geological fingerprint of the killer.
The impact itself was just the beginning. The aftermath was a true apocalypse. We're talking about gigantic tsunamis racing across the oceans, wildfires that literally stretched across continents, acid rain so intense it poisoned the seas. And then all that soot and sulfur got blasted into the atmosphere, blocking out the sun and plunging the Earth into what's called an impact winter. It got so dark and cold that plants couldn't even perform photosynthesis. The entire global food chain just collapsed.
So here's the key takeaway from all that destruction. With the dinosaurs and other dominant species gone, it created this massive power vacuum, an ecological void. The world was suddenly wide open for the taking, and who was left to claim it? Well, it was the small, scrappy survivors, creatures like our tiny, shrew-like mammal ancestors who had basically been living in the shadows, just trying not to get stepped on.
All right, so the dinosaurs are gone, the world is empty. What happens next? Evolution just goes nuts. It's like nature's experimental phase. Life started filling all those empty jobs with some of the weirdest, most incredible creatures imaginable. Seriously, some of these guys are wild.
Take South America, for example. You'd think a big cat or some kind of wolf would take over as the top predator, right? Nope, it was a bird. Meet the terror birds, and trust me, they earned the name. We're talking about 10-foot-tall, flightless killers. They were fast, they were deadly, and they had these massive axe-like beaks that could literally crush bone. For millions of years, these things were the undisputed kings of their continent.
At the same time, you had another group of mammals looking at this new world and thinking, you know what? Land is overrated. And this is where we get creatures like Ambulocetus, which literally means walking whale. I mean, look at it. It's this incredible snapshot of evolution in action. It had legs and could walk on land, but it did its hunting in the water. This was step one on the amazing journey back to the sea, a journey that would eventually produce the biggest animals to ever live, the whales we know today.
And back on land, mammals were really pushing the limits of just how big you can get. This is Intrichiltherium. It's a type of hornless rhino, and it was just enormous. We're talking over 16 feet tall at the shoulder. To put that in perspective, that's way taller than a giraffe and heavier than any mammoth. It was, without a doubt, the largest land mammal to ever walk the Earth. Nothing before or since has ever gotten that big.
Okay, so these early experiments were incredible, but they weren't the final answer, because the planet kept changing. It started getting cooler, drier, and this changing world forced life to a major crossroads, a fork in the road, really. To survive what was coming, you basically had to pick one of two very different strategies.
And this slide really lays out the two choices. This is the central conflict of the rest of the Cenozoic. Path 1. Ecological specialization. Basically, you evolve the perfect body for one specific world. You become a master of your domain. Path 2. Cognitive generalization. Instead of perfecting your body, you perfect your mind. You develop a flexible, problem-solving brain that can adapt to any world. So what's the better bet? A perfect body or a perfect brain?
All right, let's explore that first path, the specialist's gamble. So as the world cooled down, the vast forests started to shrink, and in their place, a brand new type of environment spread across the globe, grasslands. And these grasslands would basically define the rest of the era and give rise to a whole new kind of animal.
And what's fascinating is that this created this powerful feedback loop. It's a cycle that feeds itself. So the climate cools, which allows grasslands to spread. Then herbivores evolve to eat all that tough grass. But here's the cool part. All that intense grazing actually helps the grasses. It stops forests from growing back. So the animals, just by eating, were helping to create more of the very environment they were perfectly adapted for. They were literally engineering their own world. And to do this, they evolved an incredible toolkit of physical adaptations. Grass is really tough and gritty, so they developed these high-crowned teeth that just keep growing, perfect for grinding it down. On the open plains, you need to be able to run, so their legs got longer and their toes fused together to form hoofs, super efficient for running. It was an amazing strategy, but it was a gamble. It was a bet that this grassland world would stick around forever.
Okay, so that was the specialist path. But while horses and antelopes were perfecting their bodies, another group of animals made the exact opposite bet. Our own ancestors, the hominins, instead of specializing their bodies for one world, they started specializing their minds to deal with any world.
And the key idea here is something called the variability selection hypothesis. It sounds complex, but the idea is simple. The climate started going haywire. You had ice ages coming and going rapidly. The world was wildly unpredictable. So having a body that was perfectly adapted for a grassland was suddenly a huge liability when that grassland turned into a freezing tundra. The one trait that was always useful, no matter what the environment was doing, intelligence. The flexibility to come up with new solutions to new, unexpected problems.
And you don't have to take my word for it. You can see it right here in the fossil record. Look at this chart. It shows the cranial capacity, basically brain size, in our ancestors over time. It's not a gradual increase, it's an explosion. The brain nearly triples in size in just a few million years. This is the hard evidence right here. In the world of constant, crazy change, the big brain gambit was paying off big time.
So this brings us to the final showdown. The specialist's perfect body versus the generalist's adaptable brain. Which strategy was the ultimate winner? Well, if we look at the last few thousand years of the Cenozoic, the answer is pretty clear. And honestly, it's a little sobering.
Just look at this timeline. About 50,000 years ago, that super-adaptable generalist, us, Homo sapiens, shows up in Australia. And what happens? The giant megafauna, the specialized animals that live there, disappear. Fast forward to about 13,000 years ago. Humans arrive in the Americas. And again, what happens? The mammoths, the saber-toothed cats, the giant sloths, they all go extinct. You see this pattern play out across the globe. The arrival of the ultimate generalist coincided with the end of the ultimate specialists. The correlation is just impossible to ignore. And this all leads to a really powerful and kind of mind-bending conclusion. Think about it. The Cenozoic era, this whole 66 million year story, started with a force from outside our world, an asteroid that came and completely reshaped life on Earth. And now it's ending with a force that grew right here, a biological force, a single species that is doing the exact same thing. So, what a journey, right? From a world wiped clean, an ecological vacuum, came these forgotten giants. Their world changed, forcing life down two paths, one that gambled on perfecting the body and another that gambled on perfecting the mind. We are the result of that second gamble. We inherited the brain that could adapt to anything, the mind that could change the world.
So after looking back at this incredible 66 million year story, the real question is, what story will our epoch tell?
You know, when it comes to the story of humanity's first great journey, the one that took us all across the planet, there's a version we all kind of learn in school. It's a clean, simple narrative. But what if that story we all know is really just the final chapter, the last page of a much older, way messier, and honestly, a far more incredible epic?
Yeah, this is the one, right? The out of Africa theory. It goes like this. About 60,000 years ago, one big wave of Homo sapiens finally leaves their homeland. They spread out across the continents, and boom, they become the ancestors of every single non-African person alive today. A single successful push that changed everything. Except that whole tidy narrative, it's being completely torn up and rewritten as we speak, because new fossil evidence is uncovering these phantom migrations, ghost footprints left by waves of pioneers who ventured out into the unknown, tens, even hundreds of thousands of years before that successful group even existed. So let's follow that trail. Let's become archaeological detectives for a bit and look at these scattered clues that these forgotten explorers left behind, from caves in Europe all the way to the deserts of Arabia. Okay, just look at this timeline for a second. The scale of time here is breathtaking. Apodimakeu in Greece, 210,000 years ago. That's not a typo. Mislia Cave in Israel, 180,000. Theon Cave in China, over 100,000 years ago. These folks weren't just a few centuries early. They predate that main migration by a colossal amount of time. It shows us that for well over 100,000 years, our species was pushing the boundaries, trying and trying again. Let's start in Greece with this one piece of bone. In Apodima Cave, researchers found a partial skull. And after years of painstaking analysis, they confirmed something that just sounds impossible. It belonged to a modern human, and it was a staggering 210,000 years old. That one fragment shatters our timeline, pushing our species' arrival in Europe back by over 150,000 years. And this is where the story gets really wild. In the exact same cave, they also found a Neanderthal skull. But here's the kicker. The Neanderthal skull was 40,000 years younger than the human one. Just think about what that means. Our ancestors got to Europe first, they set up shop, and then they were gone. They vanished. And the area was later reoccupied by Neanderthals. This wasn't some simple one-way conquest. It was a complex dance of populations coming and going. Now let's jump over to the Levant, which has always been a crossroads at the ancient world. And here, the evidence gets even richer. We've got a jawbone from Mislia Cave that's almost 200,000 years old. And these people weren't just scraping by. No way, they were thriving. They brought sophisticated tool-making techniques with them from Africa. They were burying their dead with real ceremony, placing deer antlers on the chests of the deceased. They even made jewelry, stringing together seashells and coloring them with red ochre pigment. That's symbolic thought, that's culture, and it's happening long before we ever thought it existed outside of Africa. So, okay, we know these incredible journeys happened, but that brings up a massive question. How? How did people walk from Africa to China? The answer is pretty simple. The planet they walked across looked nothing like the world we know today. You have to completely erase modern maps from your mind. For hundreds of thousands of years, the Earth's climate has been swinging back and forth between deep freezes and warmer periods. And during the coldest of those cold snaps, the ice ages, the world was fundamentally redrawn. This number is everything. During the peak of an ice age, so much of the world's water was locked up in these gigantic continental glaciers that global sea levels just plummeted by as much as 125 meters. To put that in perspective, that's like standing next to a 40-story building and watching all the water drain away from it. And when the water drops that much, new land appears. And this just shows you how different that world was. The dry, sandy Arabian desert we see today, back then, it periodically became a green Arabia, a lush landscape filled with rivers and lakes, basically a seamless highway out of Africa. England wasn't an island. It was connected to Europe by a huge fertile plain called Duggerland. Southeast Asia was a single massive continent called Sundaland. For our ancestors, oceans and deserts weren't barriers. They were open invitations. Which brings us to the toughest, most poignant question of all. If these early pioneers were so capable, so widespread, and got out there so early, where did they go? Why did all these incredible journeys ultimately just fade to black? Well, the world they stepped into wasn't empty, not by a long shot.
For hundreds of thousands of years, it had been home to our incredibly successful cousins, the Neanderthals in Europe and West Asia, and the more mysterious Denisovans out in the East. These were smart, powerful, and perfectly adapted hominins. Our ancestors weren't conquerors walking into a vacant lot, they were the new kids on a block that was already taken. And that leads us to this key idea, a failed dispersal. It's not that these people weren't good enough. They absolutely were. They reached new continents, they built cultures, they survived for thousands and thousands of years. But in the end, whether it was due to climate shifts, competition, or maybe even new diseases, their branch on the human family tree just withered away, leaving no direct genetic trace in anyone alive today. So what made that wave around 60,000 years ago so different? Why did this group stick the landing when all the others had failed? Well, it seems they might have showed up with a few crucial new tricks up their sleeves. When you compare these groups side by side, one of the biggest differences that jumps out is technology. The early pioneers had effective tools for sure, but it was basically the same Middle Paleolithic toolkit that the Neanderthals were also using. The wave that came later, though, brought something new, an Upper Paleolithic toolkit. Think finer, sharper blades, specialized tools made of bone like needles for sewing warm clothes, and maybe even the first true projectile weapons like spear throwers. That technological edge, even if it was slight, might have been just enough to tip the scales in their favor. But, and this is where the story takes one last absolutely fascinating turn. We said they left no direct descendants, and that's true. But their ghost, it actually lingers on, hidden in the most unexpected place you could imagine. Okay, you gotta follow this closely because it's an incredible piece of genetic detective work. Step 1. Some of those very first humans out of Africa, over 100,000 years ago, met and interbred with local Neanderthals. Step 2. Those pioneering human groups eventually died out. But, and this is the key, their human DNA lived on, carried secretly inside those Neanderthal populations for tens of thousands of years. Then, step 3, the new, successful wave of humans arrives, and they also interbreed with the descendants of those Neanderthals. And in doing so, they picked up a tiny genetic echo of those long-lost pioneers. Their genes made an unbelievable round trip from ancient Homo sapiens into a Neanderthal and all the way back into a modern Homo sapiens again. Wow. So, what do we take away from all of this? What does this new, much more complicated story of our origins really tell us about, well, us? It tells us our history isn't some clean, straight line of progress. It's a story of constant striving, of countless attempts, of brave journeys that ended in heartbreak, but also of an ultimate, stubborn persistence. It's this incredible reminder that exploration and failure are and have always been two sides of the very same coin. And maybe the most profound thing is that this drive, it isn't just unique to us, to Homo sapiens. This quote really gets to the heart of it. For millions of years, from Homo erectus to Neanderthals to us, there seems to be this fundamental impulse woven right into our DNA, a relentless, unstoppable need to see what's over that next hill, to cross that next sea, to just keep pushing the boundaries of the known world. Which really leaves us with one final thought. This ancient, unstoppable impulse to explore has carried us from a little corner of Africa to every single continent on Earth, and even to the moon. It is the oldest and most fundamental part of our story. So the only real question is, where is it going to take us next?